1 minus 1t, 2 plus 8t, 5 plus 3t, 6 minus 4t, right? Or there could be a 0 in front of that t, and then it'll just be the number, right? Very good. So they're easy to recognize. When you go, oh, that's just a line. Cool. Hey, there is one other way to describe lines, besides saying the parametric equation is a line or the vector equation line. There's a third way. Like, how did we do this in algebra 2 back in high school and way back when? We just did something like this, right? And when there's a way you can write it like this, it looks kind of weird though, okay? Where you eliminate the parameter. And that's called the symmetric equations of lines. So we're going to do that with this one right here. This is the vector equation of the line. This is the parametric equations of the line, but can you write the symmetric equations of that same line? By the way, I do want to point out you won't do this nearly as often as those two. This is, you'll find you'll rarely do it this way. This would be the two ways you always describe a line. But there is a way we can do this. You go, what am I trying to do? I want to write it like this. I want to eliminate the parameter what? T. So to do this, because we want to eliminate t, yeah, and solve for t in each one. So let's do that, everyone. Let's solve for t in each one. Just go ahead, solve for t in each part. And that way we can just eliminate. All right, what's t equal to here? X, subtract the 1, then divide the what? All right, that equals 2, right? Put an equal sign. What's t equal to here? Y minus 2 over 2. Lastly,
z minus 5
over
1.
1. You don't put the 1 there. There it is. Symmetric equation line. You won't do this very often. All right, just put. You won't do this too often. In fact, this might be the last time we do it. Unless you work some of the problems out of that section. Most of the time, when it comes to calc, in terms of Calc 3, we'll be doing, we're in chapter 12 right now. We start doing integrals and stuff. We don't want to write things as vectors.
I got a
Okay,
question.
but there is a way to write it, eliminate the
So on
parameter.
the symmetric equation of the line, we don't use the angle bracket to note as a vector.
I know. No, we're really, what we did, Art, this is funny, we're writing it something like this. Like when we were y equal 2x plus 3, we eliminated this parameter t.
Gotcha.
The only thing is, there's 3 of them and it looks kind of weird, right? And that's why we won't do this too often. There's just another way to write it. The book in section 12.5, they will ask you to write some of the problems. Find the symmetric equations of the line. They just want you to eliminate the t. And that's what we did. Solve for t, eliminate the parameter, right? It just looks weird, doesn't it? Right, so there are only 2 of them? Yeah. So that's the way to do it. Okay. So great job, everyone. Hey, one more thing. This described a line, right? If they said line segment, doesn't a segment stop and start? So all we have to end, if they said, what was that last, what were the 2 points again? What was the first one? 1, 2, 5, and it went to what? 3, 4, 6. I just wanted to add this one thing. You go, well, what would I do if they said line segment that goes between these 2 points? Because the line segment starts and stops, right? Whereas the line we had before just goes on infinitely. True? All you have to do is make a little note after you did all this and just say, just take your t from, let's see, if I plug in 0, did I get the first point? Okay, where would I have to stop this? What t value would make it stop at this point? 1. That's all I'd have to add. So in this part right here, don't let it bug you. I just want to show this now. When does this become important, what I just did about a segment? Chapter 16. Because we're going to be doing integrals. We'll do doing something called a line integral. And you go, oh, what's going to be my limits of integration? You're going to have everything in terms of t. And you'll come back and go, oh, it's just going to be 0 to what? 1. To make it go from this point to this point, right? You go, is it always going to be 0 to 1? If you set up your line this way, it will be. So be interested. That'll be at the end of our course.
I didn't get you. How do you get 0 and 1 for the t?
Oh, how'd you get this? So what we did was, we just looked at this to say, what values of t would give us these 2 points? Well, we noticed, heck, you put a 0 in for t, you get this point, right? But then she realized if you just plug in a 1 in here, and to say, what's 1 plus 2 times 1? 3. 2 plus 2 times 1?
4.
And 5 plus 1 is 6. So she realized that. But I wanted to point out, as long as you did this tip minus tail method to get the parallel vector, it would always be from 0 to 1. Every time. That's what would happen. And by the way, if you ever wanted to find like 5 more points on this line, what could you do? Just make up other t values, right? You say, hey, go find 5 more points on this line. Okay, use t equal to what? Negative 10. Use t equal to 15. Use t equal to 2. You could find infinite amount of points on this line by just making up values for that parameter. Does that make sense? And you got, there it is, that line going through 3-dimensional space. So isn't this cool? So this is pretty big because we now have a way to describe a line in 3-dimensional space. So it's shocking that we didn't do what? Back in algebra class, they never taught it like this. You know, we just did 2-dimensional space. We did everything as what? Y equals mx plus b. We never wrote things like this in terms of lines, did we? But now it becomes, you know, like essential that we do that. Cool. All right, so that's lines. Hey, we'll come back to these lines. We'll come back to these lines. That was good. I now want to talk about planes. So now we have a way to describe lines in 3-dimensional space, right? It's just going to be, put the point here, put the parallel vector here, and put t's here, right? And you get the parametric equations of the line, right? So I'll leave that up here in case we get different points. Or I can just do what? You want the right, could this be our formula? Plus, 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 t, t, t. And what, I'm going to put an a, b, c in front. What's xo, yo, xo and y are x naught, y naught, and z naught. This would be the initial point, right? A, B, C would be the vector that's what? Parallel. So x naught, y naught, z naught is just one point that you got on the line. The A, B, C is the, what kind of vector? Parallel vector. It must be parallel to the line, right? And you can describe any line that way. Well, how about a plane? Well, let's just draw a plane. Plane like this. Here's a plane. Plane! To describe lines, we use a parallel vector and a point. To describe a plane, let's use a normal vector. What I mean by a normal vector, a vector that is perpendicular to the plane. So what if I have a normal vector? You can call that ABC. Alright? These are the components of the normal vector. And I'm just going to stick some 2 points in this plane. Here's a point. Alright, how about x, y, z? Will that work? Sure, there's a point in the plane. So we're deriving the equation of a plane. I'm just going to pick another point that's sitting in that plane. I don't know, how about like x naught, y naught, z naught. How can we set up an equation of the plane? This is how we describe the equation of the plane. You got this normal vector, and you got these 2 points. Can you help me get a vector between these 2 points? What would you do? Tip minus tail, right? Tip minus tail, like x minus x naught. Y. If I did like from this point to this point, I do a vector like that. Now, what do you know about 2 vectors that are perpendicular to each other? In the dot product.
0.
So we use the dot product repeatedly to describe equations of planes. Because what's going on here? It looks like this vector dot this vector equals what? That's how we do equations of planes. So here it is. Dot p equals 0. Dot product equals 0.
0, yeah.
One of the vectors is the ABC, right? What's the other vector? X minus x naught, y minus y naught, and z minus z naught. And what will this all equal to? It
0.
has to equal 0 because they're perpendicular, right? But let's write this bit, that looks weird. How about this? A times, this is what I'm gonna leave up all class. A times x minus x naught plus b times y minus y naught plus c times z minus z naught. And I don't want you to forget this on the test. Is that it? Is that the equation of plane? Hold up. Equals what? Equals 0. Equals 0. Always, dot product equals 0. Okay. What's the ABC? With a line, it was the parallel vector. What is it with a plane? It's the...
Perpendicular.
Yeah, there you go. You can call it the normal vector to the plane. You can talk about this is a vector that's orthogonal to the plane. You can call it the orthogonal vector, or you can just say perpendicular. But you need that, and then you just need one simple point. So in a secant with a plane, you need a point on the plane, and you need a normal vector to the plane, which means you need some vector that is perpendicular to the plane. You can always describe a plane. So on that note, everyone, here you go. Oh, here's my point. 1, 2, 3. Here's my perpendicular vector. Didn't I use 4, 5, 6 before? Okay, everyone. This vector is perpendicular to the plane. Perpendicular to plane is the vector, how about 7, 8, 9? Okay. Can you come up with the equation of the plane? This will be what? 7, 8, 9, x minus the what? 1, y minus the 2, z minus the done. Now a lot of you might want to distribute that, and I think we should. Sound good? But can I leave an answer like this? Someone asked me to find the equation of a plane. Of course you can. That's my equation of the plane. But students do like to simplify it. What do we get here? 7x minus 7 plus 8y minus 16 plus 9z minus equals 0, or 7x plus 8y plus 9z equals, is it 50? No, that's better. You don't have to leave it equal to 0, you can simplify it. How can I check to see if I did this right? Because I'm not going to screw up distributive property. What could I check? What would have to fit in this x, y, and z so it does equal 50? The point. You can plug that point right back in here, and it should all turn into what? 50. 7 plus 16, 23. 23 plus 27, you bet is 50. By the way, I do that all the time. I'm like, if I mess this up, I will just quickly take the point, plug it back into that equation to make sure it's working. Okay? So you can leave answers like this. Absolutely. Sometimes you may want to do this just because it looks a little bit nicer. Just don't forget that equals 0 if you do it like this, right? So we're always doing dot product to describe planes, true? But we need a normal vector and a what? A point?
So this one is called the equation to the plane.
The equation of a plane.
Okay.
This describes all points on this plane in three-dimensional space. Right? Now, how many points are on that plane?
3.
In terms of like this plane right here, how many points are on it, like theoretically? Infinite,
Infinite,
right?
yeah.
And so if you wanted to find a bunch, like, well, I could let that equal 0.
Uh-huh.
I could let that equal to 0, but then I'd have to solve for what?
Z.
50 divided 9. I could let this equal 1, this equal 1,000, then I'd have to solve for what? Z. Do you all agree? I mean, we could go all day long, just pick 2 numbers or 2 letters, and solve to see what the other, we can find points all day long. But that's what's so great about this. We have now described a plane in three-dimensional space. It could be flat, but it could be what? Nice and slanted. And we're about to get into 12.6, which is all the different surfaces. But now do you see what planes look like?
Yeah.
Most importantly, when you see planes, what do these numbers, we call them the coefficients, represent? The coefficients, when you just look at a plane, what do you know about this? They describe the components of the normal vector. That's what they describe. What's this 50? Just some number that falls on the right side, right? Who cares about that? But you know, you see equation of a plane that number, and that number had to be the what? The components of the perpendicular vector. Cool. It's interesting how often that can just help you out. You'll just go, you'll be in chapter 16 and go, man, I just wish I could come up with a normal vector to this thing, and you go, oh wait, it's 7, 8, 9. Right? There's other ways to get it, but you'll be like, oh, it'll just be 7, 8, 9. Cool. All right, well, let's try one of these. Well, can you come up with, erase all this. Leave this here. How do we describe equation of plane? A times plus B times plus C times equals 0, right? Or that's the normal vector. This is just some point on the plane. So now even from now on, I'll take this out. Because all we're saying is you just need that point, true? Hey, let's do another simple one. Make up a point.
3, 1, -2.
All right? A to make up a vector.
4, 7, 3.
Now in this vector he made up is normal, is perpendicular to the plane. Give me the equation of the plane. Find the equation of the plane where that's the vector that's perpendicular to the plane, that's the point on the plane. And we'll see the problems like this in a second. And by the way, you don't have to simplify it. So 4 times
6 minus 3,
boom, plus
7 times
y minus 1 plus